Hi everybody, very nice to be here. So I'm going to talk about large-scale clustering problems in distributed message passing frameworks, in particular MapReduce and beyond. So this is based on several recent papers I've written with colleagues at Google and others, and my main focus is on like joint work with Silvio Latanzi and Zio Zhu, which appeared in ICML, and two ongoing work with my colleagues at Google. So what's the agenda? What's the general message here? We have been trying to build so maybe better this time too. So we are trying to build a library for large-scale graph mining where we can handle like pretty big graphs with like trillions of edges and so on. And we want to build like a general purpose library that other people can use and run on like thousands of machines. So it's very important to make sure that what we develop can run under like failures of machines and so on. So it's very important to have a fault-tolerant system. So I'm going to talk about some of the activities we have had and basically the problems we face and some like research directions in the spirit of what I was asked to talk about. Basically, I'm trying to pose interesting problems. The example problem that I'll tell you the story about is the overlapping clustering problem. The ideas that I want to deliver throughout the talk, one is actually the local algorithms are very useful and important and very related to the previous talk, and I'm happy that we already heard about that. And then about algorithms that use MapReduce framework, I mentioned like some simpler algorithms, what are the metrics that one has to look at, and the use of distributed hash table service that can accelerate and like speed up the algorithms, and also like asynchronous message passing framework that can help throughout the process. So I'm going to focus on the ideas and pose challenges, like less details. And I'm like algorithmician, so I work with many engineers like in these problems, and I try to pose the problems that appear. So basically, we are trying to solve a clustering problem. What do we mean by a good cluster? A good cluster should have relatively a small number of edges going out and more number of edges inside. So one way to capture this notion is to define the notion of cut conductance, where the objective function is the cut value. So in this example, like there are two edges going out. So that's the edges between S and complement of S. And the denominator is the total volume of nodes inside the cluster. So in this example, I have two edges in the cut. And then here, the volume is the sum of the degrees of nodes in the cluster. Basically, I sum all the degrees of the nodes. So this is the notion, the cut conductance notion that I'm trying to minimize. If I minimize cut conductance, I make sure that my cluster has a small number of edges going out. And also, I make sure that I have many edges inside, because the sum of the degrees of nodes inside is big. So this notion has been this metric is has been examined, and it's like a good metric to show which clusters are good. So I'm going to talk about overlapping clustering problem. Why do I care about overlapping clusters? First of all, in many situations, natural social communities are overlapping. I can end up with better objective function, better conductance, and so on if I go after overlapping as opposed to non-overlapping clusters. They're easier to compute, and they're useful also for distributed computation. This is based on like a recent work that I did with Reed Anderson and David Gluck here. So I want to find overlapping clusters with this motivation, and by good cluster, I mean a cluster with good low conductance. I'm going to revisit this later in the talk, but that's the setting. And if I want to define one specific problem that I would like to solve, and I won't be able to solve it completely, and it's for you to solve at the end, is I want to find a set of overlapping clusters, S1 to ST, I want to make sure that I cover all the nodes of the graph, or maybe all the edges of the graph. So I want to describe the whole network. So I want to cover everything. And I want to make sure that maybe my clusters are not too big, because I want like each of them to focus on a topic, or if I want to use them for like a distributed computation, I want to make sure that they fit on a machine. And also, I want to optimize an objective function related to conductance. I can look at the conductance of these clusters, and I can try to minimize some measure of conductance over all these clusters. So for example, I can minimize the maximum conductance of all the clusters, or I can minimize the sum of the conductance, or some other measure of the conductance. Yes?
So do you consider P to be like omega of number of edges, or is it actually going down?
It could be like the square root of n or something like that. Yeah. So if I think about this type of problem from a completely theoretical perspective, and I want to give good approximation algorithms, there are like ways to give polylogarithmic approximation algorithm for these problems using some embedding to like a tree space, and like using Rocket decomposition and so on, and doing like dynamic program on trees. So in terms of multiplicative approximation, there are polylogarithmic approximations, but we wanted to solve this type of problem on very large graphs. So that's the challenge we are faced with. And the way we go about it is to produce basically local clusters around each node with good conductance. And this we can do because we use like local message passing type algorithms. And then we have to do post-processing on these clusters, join them when it's necessary, and produce like global clustering. So that's actually the main part of the talk. I'm going to talk about local clustering and how we generate these clusters, and one new theorem about this topic. I'll try to go over this a bit faster because the previous talk focused on this part. And then the global clustering part is to put together all these clusters in a MapReduce framework. So again, I'm talking about graph clustering for conductance. If I want to minimize the conductance as an optimization problem, so there are basically algorithms, spectral algorithms that achieve square root of the optimum, and there are logarithmic approximations known, and combinatorial algorithms. But these algorithms are global, so the running time of these algorithms depend linearly on the size of the graph. I don't want that. I want local algorithms. I want the algorithm to have dependence only on the size of the output, not the whole graph. So if I'm like interested in a small part of the graph, like a small cluster somewhere, I don't want to have an algorithm with running time proportional to the whole size. So let's say I have a node V. So this is very similar to we saw like in the previous talk. So let's say there is an optimum cluster A that we want to compete against, and the conductance of this cluster phi of A is psi. So we don't know A, but we know V. So we can see V and like walk around V. So at the end, we want to output a set S with conductance that's like related to the optimum conductance. So can we achieve log n times the optimum conductance? No, actually. What we can do, what one can achieve, is to achieve like similar to spectral partitioning, square root of psi. So there is a long sequence of work by Spearman Tang and then Anderson et al. That's basically that finds like a cluster with conductance proportional to square root of phi of A. So like let's focus on this page rank random walk type algorithm by Anderson, Chang, and Lang. So they can achieve square root of the optimum times some log factors. So the first thing we did, we wanted to like improve on this, and one thing we observed was that in practice it works better, and there are like these practical like type algorithms that justifies that on real data sets they work better. So one thing that we did was, so yeah, before I tell you about the our improvement, maybe I can tell you about the algorithm itself. So this is like an animation of the algorithm. So we want to find a cluster around node V. So we consider a personalized page rank random walk around node V. We compute basically the personalized page rank vectors for node V. So these are the probabilities that we will end up with if we go on a random walk with a restart of alpha at node V. So we do a random walk, uniform random walk, and at each step with probability alpha, we go back to the source node V, and with probability 1 minus alpha, we go uniformly at random to one of the neighbors. And then we measure the probability of ending up at each of these vertices. Then we sort all the vertices according to this probability, actually to normalized probability. So we go, we sort based on the probability for each node over the degree. And then we basically take into account all the sweep cuts. The first vertex, the first two vertices, the first three vertices, and so on. So the theorem is that one of these cuts has a good conductance compared to the optimum conductance. It achieves the square root of the optimum. So that's what was known, and it works very well in practice. I'm going to tell you a little bit about how we do it for all nodes at the same time and so on. But what we can show is that we can go beyond the triggers gap, basically the spectral gap, and we can relate the performance of these algorithms with another notion, which is not only the conductance, this is the conductance of the cluster, so we also relate it to another notion that we call connectivity of the set S. So let's understand this.
So doesn't Anderson channel line have a root login as well?
So yeah, there are tildes here.
So is there a tilde in your result as well? Or?
Yes. Everywhere, yeah. Everywhere there are logins. So there are improvements to that. Yeah, just to. So this is let's look at this type of cluster. The conductance of this cluster is this cluster S is there is one edge going out, but this is not a good cluster because you can divide this cluster into two pieces and get a better cluster. So this cluster has a small conductance, but it has also a small connectivity, because if I look at inside this cluster, there is another cluster with a small conductance. So what happens is that this other cluster, S prime, has this property that it has a small conductance, but it has large connectivity. So I can't cut this cluster into two pieces. So arguably, this is a more robust notion for a good cluster. And that's what we call connectivity. And our result shows that we can get a square root of the optimum conductance, but at the same time, we can use this random walk type algorithm to achieve the conductance over square root of the connectivity of the set. Let's take questions after. So in particular, we show if the gap between the connectivity inside and the connectivity outside, the cut conductance, is big. So if the cluster is very well connected inside and not well connected outside, then we can basically go beyond a square root of phi. So if I want to show you in formulas, so if I wanted to get a global algorithm, there was a previous result that shows you can get order of phi over square root of lambda 3. What we get is this formula, which is basically a square root of phi over the gap if the gap is large. And we can also show that this gap that we get is optimal among all random walk-based algorithms. So no matter how you change the teleport probability, the performance of the cut that you get is not better than this. So
by
that
random walk algorithms, you mean one parameterized as k-rank with the teleportation function?
Yeah. So in order to get this result, we only change the teleport inequality, probability, basically. So I have some practical results on this, but I want to get to the second part. So this is also to emphasize that what we compute is personalized PageRank vectors for all pairs of nodes. So we don't do it only for one node. We can do in parallel, starting from all nodes all together, and we can actually take advantage of this thing that we can do recursive computation. We don't compute exact PPR vectors. We compute approximate vectors, and there are good algorithms to do that. And this is to show that the algorithm is very simple to implement using some push flow type algorithm. So they can be in particular implemented using MapReduce type algorithms. So the first challenge that I'm trying to pose here is to understand local message passing type algorithms, but go beyond the cut conductance objective function. Maybe we can look at density, what we looked at was connectivity, or other objective functions, like your favorite objective functions. Now we have these overlapping, like we compute one cluster for each node. We want to combine them. So what we do is we construct a graph over these overlapping clusters. If there are two clusters that overlap a lot, basically we want to put them together. So one way to do it is to construct this graph and then compute connected component in this graph. So that's what I'm trying to do. So I want to understand global clustering, but very simple clustering, like connected component computation or hierarchical clustering of these type of big graphs. So if I want to compute, for example, connected component, the most basic clustering, what I can do is I can keep track of a set of IDs for each node B. So each node B maybe is trying to have the minimum ID of the node in its cluster, in its connected component. So there are simpler algorithms like hash-min algorithm is where each node keeps track of the mean ID, and it sends the mean ID to all the nodes in its current component. The hash-to-all algorithms is where all nodes in the connected component send basically this type of message, their current mean ID, to all other nodes in the connected component. There is a hash-to-min algorithm where the minimum ID node in the cluster send message to all nodes, and all nodes send message to the minimum ID. So there are these other different type of algorithms that have been considered by Rastogi et al. How do they perform in practice? For a MapReduce algorithm, the most important thing that we care about is the number of MapReduce rounds. So they, like hash-min algorithm, may take a diameter number of rounds, so it's not interesting. It turns out the hash-to-min algorithm, which is not easily analyzable, has a very good performance. This is the algorithm where each minimum ID node keeps track of all nodes in this component, and all nodes keep track of only the communicate with the minimum ID. But the question was, how can we improve on these type of algorithms and have provable bounds? So what we observed was that there are two other important measures that one has to take into account. One is the total communication cost that we pay throughout all the MapReduce rounds. So it's not only the worst case bound on one MapReduce round. Maybe if you have log n rounds even, it's important if you amortize, you have constant per round. And then the load balancing issue is when we do map and reduce, we want to make sure that the reducer doesn't get too many messages. Each reducer doesn't get too many messages. So I'm assuming that we know MapReduce because the previous workshop had MapReduce description and everything. I didn't have time to put all. So inspired by these objective functions, we ended up using another type of algorithm that basically combines these two operations. The small star operation basically makes sure that each node, for each node, all the nodes that are neighbors and have less, the ID less than that, connect to the minimum ID connected to it. And the large star operation does the opposite. So this type of operations make sure that the number of edges that we deal with at each step does not increase. And this type of operation makes sure that if you do this operation at all nodes, even though here you lose connectivity, if you do it at all nodes at the same time, you don't lose connectivity across the whole graph. So because of these good properties, we can run this type of simple algorithms and what we get is like an alternating hash greater to mean, hash lesser to mean. It has good theoretical properties. In particular, the total communication is good, and for random graph, it's linear. But in practice, for like very big graphs, it performs up to 10 times better than the simple hash to mean type algorithm. And then, like if we just optimize it a little bit by making sure that none of the reducers take too many messages, we can just improve it further. So the first idea is basically making sure, even though the number of rounds go up, if the total communication goes down, it does help. The second idea was to use a distributed hash table service. And like these two loops that we implement, we can implement the inner loop basically in memory as long as the number of active IDs of the connected components is below some number. So we know that after a couple of rounds, the number of active IDs of the connected component that we deal with goes down drastically. So we can keep it in memory, and that will help a lot. So we can get order log n, again, MapReduce rounds, and we can improve the running time by a big factor. So there are some practical basically speed ups that I can show you, but it was basically very much summarized in the first two slides. So let me get to the second challenge slide, which is basically for MapReduce, the connected component in MapReduce. The interesting theoretical problem is to solve the connected component problem in constant number of rounds, or prove that this is not possible to do. And this, another message I want to deliver is when we design MapReduce-based algorithms, we care not only about number of rounds, but also total communication across the whole running time, and also congestion of each reducer. Then the very last slide in the next 1 minute I have is a new distributed computation framework in which we try to implement a completely asynchronous message passing framework. So for connected component, what we do is for each node we keep track of the minimum ID of the node in its connected component, and this node propagates its minimum ID to all the neighbors, but in a completely asynchronous manner. So each machine takes care of some number of nodes, and it has a priority queue, and it decides which messages to send, and so on. So we do this until we converge. No node can is willing to change its state. So this is not MapReduce. If we wanted to do MapReduce, we had to do synchronized steps. So the advantage here is that we don't need to wait for other nodes. But then it's very important to make sure that we have fault tolerance, and we have asynchronous message pass, asynchronous checkpointing. So once in a while, each machine stores its data in case when it goes down, it can recover the data. So this is the simplest type of algorithm we could implement without any optimization. And the interesting thing was that even this first version of the algorithm, the simplest type, improved over all the optimization that we did in the MapReduce framework. So we could get 60 times faster running time and more scalable run for these compared to the externally available hash to mean implementation. So the message here is that sometimes asynchronous message passing time framework can help a lot, but if we want to make sure that it works, in order to ensure fault tolerance, we need to have a self-stabilizing type algorithm that if a machine fails and you restore the state, this has to converge to the right solution. And we can afford to have maybe very small state for each node, in particular maybe constant size state for each node. So if one can design an algorithm of this with these restrictions, it seems to work very well in practice, and I have 2-3 other examples of success stories like this that I can tell you. That's all. I think I skipped the overlapping clustering part, the wrap up. So I just want to basically conclude by saying local algorithms are very useful. please like design more algorithms for other objective functions. Like in use of MapReduce, use of distributed hash table service can help a lot. And like computational models that takes into account distributed hash table service on top of the MapReduce is important. Asynchronous message passing, bit fault tolerance is another important topic that will be useful in practice. And for overlapping clustering, I posed the problem at the very beginning, and I gave you some theoretical results, and then I gave you some way of computing this in practice. For each step of what the algorithm that I designed, I could give you some theorems and so on. But end to end, if I wanted to design a good overlapping clustering algorithm that optimizes that objective function and runs like for very big graphs, I don't have any theorem. So the first challenge is to have a good algorithm that can be run in practice. It's based on these local algorithms in MapReduce framework, etc., etc., and we can prove some good properties. And I want to avoid like random graph models and so on as much as possible. Like, yeah, great, thanks.
Questions?
Yes.
There are other questions. So for the 10 billion graph, public graph, what are the timings for preventing clustering? Say with, I don't know, the number.
So what I reported was a speed up over a baseline algorithm that has been implemented in Hadoop. So I was careful not to specify like exact running times. I can tell you.
Have an idea.
I mean, like less than a couple of hours.
Okay.
Yeah, but yeah, we can talk like offline more. I didn't want to.
Okay.
Okay, so maybe we can.
And these apply to like big graphs that are static or that are constantly
very
changing?
good question. So this is all about the static graphs. And if you ask me about like what type of graphs I'm talking about here, it's like 20 different types of graph. It could be like YouTube videos with like two videos are connected if they're co-watched by the same people. There are keyword graphs, there are advertiser-based graphs, there's G+ graph, and so on. So we have like many graphs that, yeah.
You want to say that while the video's on? How many graphs?
No, that's fine. So yeah, like we work with many different type of graphs, and sometimes, yeah, like social graphs have like a different behavior. So for example, we have image graphs where we have an edge between two images if they are like similar, visually similar. And there, the way that we compute the graph also becomes important because we can't put all the edges there. So we have to take into account the way that the graph was computed when we want to make an assumption in the clustering phase. Yeah.
Thank you.